Hello everyone, welcome back. Today we're going to discuss a short summary of SN1 versus SN2 reaction mechanisms. And I'm glad that you could be able to join me, and we'll have more live broadcasts of a selected summary of topics in organic chemistry. And I want to just kind of tell you heads up that in the fall semester I'm going to go through Organic 1 in a live broadcast. Hope you should be able to join me. But as a test run, I'm going to discuss some SN1 versus SN2 reaction mechanisms in this broadcast. I have already posted solved problems of SN1 and SN2 as well, and a lecture as well. So I really encourage you to go to the links that's attached in this presentation and review all the SN1 and SN2 reaction mechanisms. This is really a summary of what I have already showed in those videos. So looking at SN1 versus SN2 reaction mechanisms, I think it would be a good idea for me to just show you the energy diagrams associated with the reaction mechanisms of SN2 first, and we're going to discuss also the SN1 reaction diagram. So SN1 energy diagram, if we start with SN1, it is a multi-step reaction, as you know, meaning that it's not a single concerted reaction mechanism. And as you see here in the energy diagram, here is the starting materials, and the starting material gets activated, and the reaction in the transition state holds a very activated, highly energetic transition state species, which is in the alkyl halide. The halide starts bond between carbon and the halide starts to elongate. That means it's about to break. So that is the transition state. So the initial activation of the alkyl halide is actually the rate determining step, where it's activated and the elongation and finally leaving the carbon bond, the carbon X bond. So the generation of the carbocation would be, and let me do here, is actually the rate determining step. So that is the slowest step in the S1 mechanism, formation of the carbocation. That is the rate determining step, RDS. Here is this transition state, high activation energy. That's why it is the slowest step in the follow-up to make the bond. Consequently, if you just see the rate law, because the rate determining step involves only the alkyl halide, it is the rate law is just dependent only on the alkyl halide. So the nucleophile here is zero order, meaning that it doesn't have any consequence in terms of the rate law. The rate law is only dependent on the concentration of the alkyl halide. So whatever the concentration of the nucleophile is increased or decreased, the rate will not be affected. Here it is order 1 with the alkyl halide. So once it reaches to the transition state, it forms the carbocation. This is the intermediate in the SN1. This is a transition state, activated complex. We call this activated complex. And here it is the intermediate. Okay? So once you have the intermediate, no matter how strong the nucleophile is, it doesn't take much of it, whether the concentration high or not. This recombination happens at this stage. The nucleophile comes and start to attack this intermediate. To make this secondary transition state, the nucleophile carbon bond is being formed, and finally you create the nucleophile completely attached to the electrophile, and you have the leaving group, of course, left the alkyl halide. So overall, this is just an example where the reaction is presumed to be exothermic, because here you have a delta H, which is less than 0. It could be endothermic as well, but here, as an example, we have an exothermic SN1 type reaction. So really what determines in the rate of the reaction would be the formation of this carbocation. That means the stability of the carbocation is important in SN1. Stability of carbocation. The carbocation is very important. So in most cases, the alkyl groups are important. Let's say you have 3 different alkyl groups. In general, alkyl groups are electron donating. They're electron donating to the carbon center. That's how the stability comes. So tertiary is much faster than secondary, and almost no reaction is in a primary in SN1 type reaction. For SN1, this is order. A tertiary alkyl halide is much faster. So this is the fastest because the carbocation that forms from a tertiary is much more stable. So I have already dealt with this in detail in the lecture section. So I'll just pass to the SN1 energy diagram. So the energy diagram for SN2 is much more simpler because the reaction is a concerted step, concerted or single step reaction. It is just a backside attack of the electrophile with a nucleophile. So if you have a nucleophile here with a negative charge, plus if you have CH2X, for example, the nucleophile with a pair of electrons comes from behind that carbon, not that whole thing, but I should write actually just the carbon that contains the alkyl, the halide, comes from back attack, and the alkyl halide leaves. That's what you see here in the transition state, because the alkyl halide as well as the nucleophile are implicated in the transition state. That means both are implicated in the rate determining step. That's why here in the rate law, both the alkyl halide and the nucleophile are implicated. So it's first order with alkyl halide and first order with the nucleophile. That means changing any concentration of a nucleophile or an alkyl halide would affect the rate. For example, if you have alkyl halide concentration increased by 5 times and the nucleophile changes by 5 times, the rate overall changes by 25 times. So both are important in the rate law. So what happens is the nucleophile comes in, attacks this the nucleophile, the electrophile would be attacked, and creates this penta-coordinated transition state. Penta-coordinated. So it's very crowded. Hence, it is sterically sensitive for the rate. That means it doesn't, for example, if you have a tertiary one, the structure would be so crowded that the rate would be very high, the rate would be very low, the reaction would not even happen. So unusually, the transition state, which is sp3 hybrid carbon with penta-coordination, is not a common thing. So that's why this is a very high activated complex, very high energy state. So this is penta-coordinated, and if you remember for SN1, it is tri-coordinated planar structure. That has a consequence in the stereochemistry as well. So with this, you can see here the rate law is both nucleophile and alkyl halide are important. Carbon is penta-coordinated, crowded, so sterics is important. So the rate is methyl halide is much greater rate because it's very small, and the rest are hydrogens, so there is no steric crowding, as you see here for a methyl halide. The rate is much, much higher than the primary, secondary. It is the reverse is compared to the SN1. Tertiary almost doesn't go through SN1, SN2 type mechanism. So these are clear distinction of SN1 and SN2. So the energy diagram you should be familiar with. It has a lot of information. It has the rate, what the transition state looks like, and in terms of stability of the transition state. This is very fast. This is almost no reaction. The tertiary alkyl halide doesn't go through a SN2 mechanism. Secondary is borderline. It could go SN2, SN1 as well. So these are the two energy diagrams we just discussed. And let me just give you actually a summary of this in a tabular form so that it will be much easier for us to just see the two differences in SN2 and SN1. So this is my comparison table. This table is a good summary of SN2 and SN1 reactions. When it comes to mechanism, for SN2, it is a single-step reaction. We just have already discussed. This is concerted. It is a backside attack. It is just a backside attack. That's how it happens. This is a two-step. That means there is a two-step. An initial step, which is a rate-determining step, is carbocation formation followed by nucleophilic attack. So two steps. Carbocation formation, the rate-determining step, happens, and then nucleophile attack comes as a second step. Okay, and the nature of the alkyl halide, of course, is also important because SN2 is a backside attack. It forms penta-coordinated transition state. So sterically, the less sterics, the better in the reactivity. So here the sterics is important. sterics factor. Sterics factor involves in this. So that's what makes the rate to be fast or slow. So the methyl, as you know, is the fastest, and the tertiary is almost no reaction as SN2 for the tertiary alkyl halide. Here in the SN1, it is the reverse, because you should form a carbocation. The stability of the carbocation is highest with this, and slowest with this. So you don't form methyl carbocation, very unstable, because electron donation from the alkyl groups stabilizes the carbocation. So carbocation stability is important. That's why you see that order, stability, because electron donating groups are the alkyls are electron donating groups to the carbocation, which stabilizes the carbocation. Okay? Let's see rate equation. We have already said that it is a second order reaction. This is second order. Because alkyl halide is first order and nucleophile is first order. Both affect the rate of the reaction. For SN2, that's why this is second order. So, the rate is determined by both the nucleophile, concentration of nucleophile, and concentration of the alkyl halide. Okay? Here, at the rate determining step, only the alkyl halide is implicated, therefore it is first order. This is first order, and it's only dependent on the concentration of the alkyl halide. No matter whether you use a very strong nucleophile, weak nucleophile, high concentration of nucleophile, or low concentration, the rate really is affected by concentration of changing the alkyl halide. It doesn't depend on the concentration of the nucleophile. And stereochemically, if you have a purely chiral compound, that stereogenic center, the effect is at the stereogenic center if it contains, let's say, if R is stereogenic center, not R, but the carbon that contains the alkyl halide, if it is a stereogenic center, okay, let's say it's H and let's say it's D. If it is chiral, then in the SN2 reaction, since it has to come from backside and this has to leave, the stereochemistry would change. So if it was R, it should go to S. If it was an S compound, it should go to an R. So there is inversion of configuration. The stereochemically, you should be aware that if you run an SN2 reaction on a stereogenic center, a chiral center, that chiral center would not remain intact. It would be affected. So inversion of configuration happens. So R goes to S, S goes to R. Okay? Okay, let's see SN1. SN1, as I already told you, it goes through a carbocation. If you have, for racemization, how it happens is, if you have a carbocation, and if you have R here, if you have R prime, and if you have R2 like this, in case of tertiary, which is always that happens, this now is sp2 hybridized carbon, and it is planar also. It is flat. This is sp2 planar molecule, planar transition state complex. Okay? So what happens in the SN2, the nucleophile has a 50-50 chance to come from top, or the nucleophile can come from bottom. That means if it was R or S, it becomes 50% R, 50% S racemization. So it will lose its optical activity, actually. So because of this, the product has no optical activity. No optical activity. Okay? So it is 50% R and 50% S. It loses its optical activity. Racemization, that's what we call racemization. Nucleophile. Nature of nucleophile is important. For both of them, the product could form, but usually the SN2 favors a much stronger nucleophile, strongly basic ones. But for SN1, because the carbocation kind of stays in the transition state for some time, a weaker nucleophile is better, so that the product exclusively forms from that weak nucleophile. So here, strong nucleophile, especially if it is fully negatively charged, that is a better. Here, usually, if you have neutral molecules like H2O, is fine also. Methanol, like solvent type, and ammonia, not fully negatively charged even can work. I'm not saying the other nucleophiles would not work. If it's strong, it would work, but it favors, in terms of formation, it favors the weak nucleophile. Okay? Now, let's see the living group. Obviously, both needs a good living group. So, both, you need something for both SN2, SN1 need to have a good living group. Good living. You need good living group. Okay? So that's the differentiation between the two. Now it becomes solvents. Solvents are also important for SN2 as well as SN1. Remember, both need polar. This is common. This is common. Polar solvents are required for both of them. The only difference here is this doesn't need a proton source or hydrogen, because it doesn't like the nucleophile to be hydrogen bonded. So it needs aprotic. The aprotic would just capture the cation, makes available the nucleophile easily. So what are this kind of solvents? Let me write them out here. DMF, I'm just giving you an example. Dimethylformamide, THF, tetrahydrofuran, DMSO, dimethyl sulfoxide. What else? DMF, THF, DMSO. These are a kind of solvents we call aprotic solvents. So you can use one in the SN2. We have, mostly they contain hydrogen that can hydrogen bond. So all alcohols, ROH. Example would be like T-butanol, for example. tertiary butanol, let's say ethanol, methanol, water even, protic solvents, and alcohols. So all protic, polar protic solvents are good in the SN1 type reaction. So this is how the reaction goes. So I'm sure together with the lecture I have already posted the problems I have solved on my channel, and I have attached in this video description as well the links to all of the discussion I have. I have solved several problems which really summarizes all of this SN2, SN1 reaction with a great discussion that would help you to master the subject of SN1 and SN2 would be helpful. So with this, I would be concluding by saying that next discussion would be on elimination reactions. So I'll be posting soon, and I will invite you to the next live event, which I will have on Sunday, on a selected topic of organic chemistry. You can email me your questions at stampdoctors@gmail.com. stampdoctors@gmail.com. I will be glad to answer your questions, and please share this with all your friends. This coming fall, I will have a live course on organic chemistry 1, which I have most of it is in my channel at Stamp Doctor, but we'll have more during the fall semester starting end of August. So thank you for listening. Please share and like the channel, and send me your questions. All your questions I will just look at them and send you a response. Thank you for listening. Thank you.